All right, Algebra 1, we're going to finish up our 2-2 notes today with section 2-2D. So let's review our factoring difference of two squares, what we had done in the 2-2C notes. So remember, when we are doing our difference of two squares, or dots, we ask ourselves three questions. One, is it a difference? Two, are there two terms? And three, are they both perfect squares? So that's what dots kind of means, difference of two squares. So first of all, is it a difference? Yes, there's a minus sign. Are there two terms? Yes. Are they both perfect squares? Yes. 9 is a perfect square. X squared, because it's raised to an even power, is a perfect square. And 25 is a perfect square. So then we ask ourselves, what times itself is 9? Well, that's 3 times 3. What times itself is x squared? That's x times x. So we know our parentheses will start with 3x. What times itself is 25? And that's 5. So they both end with a 5. One's a plus, one's a minus. So here you go. That's what your answer should look like for your bell ringer. 3x plus 5, 3x minus 5. And again, that could be mixed. You could have 3x minus 5, 3x plus 5. They could be in the opposite order. It doesn't matter. What the important part is that the parentheses are identical. One's a 3x. It starts with a 3x. They both end with a 5. One is a plus, one is a minus. It doesn't matter which one is which, okay? Now, what we're doing today is we're going to put 2-2A and 2-2C together, okay? So there are times when expressions can be factored more than once. All right, so our first step in any kind of factoring is to see if we have a GCF. That's always our first step. So what's going to happen is we look at this and we say, all right, well, there's two terms, so right away I'm thinking dots, right? So it's a difference, yes. There's two terms, yes, but are they perfect squares? That's where we run into a problem. 3 is not a perfect square. There is no number times itself that will give you 3. There is no number times itself that will give you 27. So then what we have to do is we have to say, all right, well, let's see, can I take something out of here? Yeah, I can take a 3 out, right? So divide 3 out. So I'm left with x squared minus 27 divided by 3 is 9. So now I have a difference of two squares. X squared is a perfect square that's being subtracted, and 9 is a perfect square. So this 3 is my greatest common factor. That will stay out front. And now I will do my two sets of parentheses. Okay, what times itself gives you x squared? That's x times x. What times itself is 9? That's 3 times 3. 1 is a plus, and 1 is a minus. There is your final answer. So, like I said, all we're doing here is we're taking two concepts that we already learned, the greatest common factor and the difference of two squares, and we're putting them together into one problem. All right, let's do another one. I already have the GCF factored out here for you, but if we look at this, we say, all right, it's a difference. I have a minus. I have two terms, but are they perfect squares? No. No number times itself will give you 6. Okay? So, talking about real numbers, we can get into irrational numbers, but no real number, this is 2 times 3, and no number times itself will give you 96. So that means we had to factor something out. So I factored a 6 out. So 6x squared, if I divide a 6 out, I'm left with x squared, and then minus 96 divided by 6 is 16. All right, so now I'm ready to do my difference of two squares because this part right here is a difference of two squares. It's a difference minus two terms, and they're both perfect squares. X squared is a perfect square, and 16 is a perfect square. That's 4 times 4. Don't forget that this 6 out here that we factored out is still part of our answer, so bring that down. Two sets of parentheses. And now this right here gets factored. What times itself gives you x squared? That's x times x. What times itself gives you 16? That's 4 times 4. One of them is a plus, doesn't matter which one. One of them is a minus, make it the other one. There's your final answer. Okay? Next up, now we're getting into some variable ones as well. So we not only have a number that needs to be taken out, but also a variable. So again, difference, yep. Two terms, yep. Perfect square, nope. 7's not a perfect square. So we have to take a 7 out. But also, look, x cubed is not a perfect square. Remember, when you're dealing with variables, perfect squares for variables are even powers. This is not an even power, this is an odd power. So that means we also have to take a variable out. So smallest power of x is just x, so take an x out. So what are we left with? Well, 7 divided by 7 is 1. If I started with x to the third and I took 1x out, I'm left with x squared. Minus 700 divided by 7 is 100. I started with an x, but I took that x out, so I have no x's left. So that is my first step. This right here is my step of doing the GCF. Okay? Now my next step, so that's your step 1. Step 2 is your difference of two squares. Okay? Now when you're doing your difference of two squares, don't lose the GCF part. That 7x is still your part of your answer. But now we need to do the difference of two squares here, and I will change the color for that so you can see what's being done here. Actually, let me do that over here also so you can see. We'll just color code everything. All right, so x squared minus 100, that's a difference of two squares. It's a difference being subtracted. Two terms, x squared and 100, two terms. They're both perfect squared. My variable now has an even power, so that means it's a perfect square. And 100 is a perfect square. That's 10 times 10, so let's fill it in. X times x gives me x squared. Like I just said there, 10 times 10 gives me 100. One's a plus, one's a minus. So there's your final answer, and we are finished. Okay, if you're feeling pretty comfortable with these and you want to go ahead and give the last two a try, you can go ahead and do that. Pause the video, work out example D and E. There's another one on here too, F. If you want to try those three, go ahead. I'm going to do example D with you because this one, it kind of looks a little tricky and it's a little different because we do have another variable at the end here. But if you feel pretty comfortable with it, you can go ahead and try those if you want. Or you can just stay with me, that's up to you. Okay, so again, step 1, GCF. What do we do? Look at your numbers. Can I take a number out here? Yeah, I can take a 5 out. Let me go back and keep my colors the same. I can take a 5 out. Can I take any x's out? Well, I should be able to take an x out because this is not a perfect square, it's an odd power. And I can, because this is an x, I can take an x out. Can I take an a out? Well, no, this one doesn't have an a, so that's fine. Plus, this a has a power of 2, so that means it's a perfect square, so that one's okay. Okay, what am I left with? I took the 5 out. I started with x to the 5th. I took one of those x's out. So I'm left with x to the 4th minus 125 divided by 5 gives you 25. I started with an x, but I took that x out, so there's no x's here. But I do still have the a squared. Now this is where it's a little different because we have not seen something where there was a variable on the right-hand side yet, okay? The process is the same, it's just a little bit different because we haven't seen it yet, so just stick with me here and you'll see it's not that much different. So first of all, let's rewrite our GCF, 5x. Now we're ready to do our difference of two squares. It's a difference. I have two terms and they're both perfect squares. Variable raised to an even power, that's a perfect square. 25 is a perfect square. And a, another variable raised to an even power, is a perfect square. So I'm ready to do my dots. Same way. What times itself gives me x to the 4th? X squared times x squared. What times itself gives me 25? Well, that's 5 times 5. And now here's where it's a little different. What times itself gives me a squared? And that's a times a. So that second term of 5, because there were two terms here, right? The 25 and the a, there were two terms here. There has to be two parts to this term. There has to be two parts to the term down here also. Okay, one's a plus, one's a minus, doesn't matter which one goes where. So that's your final answer for example D. Okay? Now, E and F are a little bit different as well. So I did a couple of these steps here for you. E, I just did one step, but F, I did 2 steps for you. And then I'm going to finish it out. Because what we have to remember is that there may be multiple steps of factoring, but they might not be like a GCF and then a dots. It may be something like this. So there is no GCF here, right? So we look at this and we say, well, this is just a difference of 2 squares. How is this any different? Like, how is this different than the dot stuff that we did in section 2.2c? Well, let me show you. It's a difference. There's 2 terms. This is a perfect square, and this is a perfect square. So we factor it, right? There's nothing different there. I haven't done anything different here yet. But this is not my final answer. So let me show you how this is different. And it's different because this term right here is not completely factored. This is actually a difference of 2 squares. This is a dots within the difference of 2 squares here. So sometimes when we factor a difference of 2 squares, we end up with something that has difference of 2 squares in it again. So we have to finish factoring this out. So what I'm doing here in red is just what I have underlined in red. What times itself gives me x squared? Well, that's x times x. What times itself is 4? Well, that's 2 times 2. One's a plus, one's a minus. Now, I know some people are going to look at that and say, well, yeah, so then this is a difference of 2 squares too, so there's another x plus 2x minus 2. But remember, difference means subtraction. This is not subtraction, this is addition. So this does not factor, this is prime, so we will just bring that down. Okay, that one, this one right here is not changing at all, so we will just bring that down. Okay, so this is the main one right here that you have to look out for. Sometimes we have a difference of 2 squares within a difference of 2 squares, and we have to continue factoring that. So we have that again here, but now this one's like 3 steps. So we have GCF, difference of 2 squares, and difference of 2 squares. So let's go ahead and do this last one here, and then we'll finish it up. So first of all, we can take a 2 out. So we divide a 2 out. We can take a 2 out of both of these. I'm left with x to the 4th minus 2 divided by 2 is 1. So don't forget that 1 there. Now, a lot of times people look at this and they say, well, there's no difference of 2 squares. 1's not a perfect square. 1 is a perfect square. It's just 1 times 1. So now we're going to factor that into 2, bring the 2 down, x to the 4th minus 1. X to the 4th is x squared times x squared. 1 is 1 times 1. So we get 1's a plus, 1's a minus, right? And again, this is another difference of 2 squares. X squared is a perfect square. 1 is a perfect square, and it's being subtracted. This one is not because it's being added. That's a sum. That's not a difference. So our last step here, bring down the 2. X squared plus 1. Again, this term right here is just being brought down because that can't be factored any further. But x squared minus 1, this can be. X times x is x squared. For 1, we have 1 times 1. 1's a plus, 1's a minus. So that is your final answer here for this last example. Okay, so again, we're adding section 2.2a and 2.2d, putting those two together into one type of problem. So multiple steps of our factoring here coming together. So if you have any questions on that, like always, send me a private comment, send me an email. Let me know if you have any questions on this. And if you're confused on anything, just send me an email and let me know, and I will get back to you.